Study of ethers is divided into five main categories. The first one is classification. The second one is physical property. The third one is nomenclature. The fourth one is chemical reactions. And the last one is preparation. Click on the corresponding buttons to learn more about ethers. Let's understand classification of ethers. Ethers are classified as simple or symmetrical and mixed or unsymmetrical. The example of simple or symmetrical ether is CS3OCS3, that is methoxymethane. An example of mixed or unsymmetrical ether is C2H5OCS3, that is methoxyethane, and also C2H5OC6H5, that is ethoxybenzene. Simple or symmetrical. Alkyl or aryl groups attached to oxygen atom are same. Simple or symmetrical. Alkyl or aryl groups attached to oxygen atom are same. Mixed or unsymmetrical. Alkyl or aryl groups attached to oxygen atom are different. Physical properties. Let's understand physical properties of ethers. CO bond in ethers are polar and thus ethers have a net dipole moment. For example, C2H5O C2H5. The net dipole moment is directed towards oxygen. The weak polarity of ethers do not appreciably affect the boiling point, which are comparable to those of the alkanes of comparable molecular masses, but are much lower than the boiling point of alcohols. For example, CS3CS2CS3, that is normal pentane, C2H5O C2H5 ethoxyethane, and CS3CS2OH, that is butane 1-ol. Their boiling point follows the order 309.1, 307.6, and 390, respectively. The miscibility of ethers with water resembles those of alcohols of the same molecular mass. For example, ethoxyethane and butane 1-ol. This is due to the fact that, just like alcohols, oxygen of ether can also form hydrogen bond with water. Let us now understand nomenclature of ethers. Common names. Common name of ethers are derived from the names of alkyl or aryl groups written as separate words in alphabetical order and adding the word ether at the end. For example, common name of CS3OC2H5 is ethyl methyl ether. If both the alkyl group are the same, the prefix di is added before the alkyl group. For example, the common name of C2H5OC2H5 is diethyl ether. IUPAC system. Ethers are regarded as hydrocarbon derivatives in which a hydrogen atom is replaced by an OR or OAR group, where R and AR represent alkyl and aryl groups, respectively. The larger group is chosen as the parent hydrocarbon. So, the IUPAC name of CS3OCH2 CS2 is 1-methoxypropane, and its common name is methyl N-propyl ether. The IUPAC name of CHCS3 whole twice OCS3 is 2-methoxypropane, and its common name is methyl isopropyl ether. This table shows common and IUPAC names of some ethers, which are listed below. Let us now understand chemical reactions of ethers. The first one is cleavage of CO bond in ethers. Ethers are least reactive of functional group, and cleavage of CO bond takes place in drastic conditions with excess of hydrogen halides, that is HX. The reaction of dialkyl ether gives two alkyl halide molecules. That is, consider the reaction ROR plus HX gives RX plus ROH, and ROH plus HX gives RX plus H2O. Ethers with two different alkyl groups are also cleaved in the same manner. For example, the reaction ROR plus HX gives RX plus R-OH. Text. The order of reactivity of hydrogen halides is as follows: Hi greater than HBr greater than HCl. The cleavage of ethers takes place with concentrated Hi or HBr at high temperature. Alkyl aryl ethers are cleaved at the alkyl oxygen bond due to the more stable aryl oxygen bond. Consider the reaction C6H5OR plus HX gives C6H5OH plus RX. Stability of phenyl oxygen bond is due to partial double bond character. Elaborate. You can here see the stability of phenoxide ion, that is through resonance. When one of the alkyl group is a tertiary group, the halide formed is a tertiary halide. Consider the reaction CCS3 whole thrice OCS3 plus HI gives CS3OH plus CCS3 whole thrice I. It is because in step 2 of the reaction, the departure of leaving group, that is CH3OH, creates a more stable carbocation, that is CCH3 whole thrice positive, and the reaction follows SN1 mechanism. Mechanism. The reaction of an ether with concentrated HI starts with protonation of ether molecule. Iodide is a good nucleophile. It attacks the least substituted carbon of the oxonium ion formed in step 1 and displaces an alcohol molecule by SN2 mechanism. Thus, in the cleavage of mixed ethers with two different alkyl group, the alcohol and alkyl iodide formed depend on the nature of alkyl group. When primary or secondary alkyl group are present, it is the lower alkyl group that forms alkyl iodide, that is SN2 reaction. Step 2. I plus CH3OH positive CH2CH3 gives I CH3OH positive CH2CH3 whole negative, which gives CH3I plus CH3CH2OH. When HI is in excess and the reaction is carried out at high temperature, ethanol reacts with another molecule of HI and is converted to ethyl iodide. The step 3 of the reaction is CH3CH2OH plus HI reversible CH3CH2H2O positive plus I minus. I minus plus CH3CH2H2O positive reversible gives CH3CH2I plus H2O. The second method is electrophilic substitution. The alkoxy group, that is OR group, is ortho para-directing and activates the aromatic ring towards electrophilic substitution in the same way as in phenol. The resonating structures of C6H5OR is given as follows. Phenylalkyl ethers undergo usual halogenation in the benzene ring. For example, anisole undergoes bromination with bromine in ethanoic acid, even in the absence of iron, that is 3-bromide catalyst. It is due to the activation of benzene ring by the methoxy group. Para isomer is obtained in 90% yield. Consider the reaction C6H5OCH3, that is anisole, in presence of Br2 in ethanoic acid to give para-bromoanisole, which is major product, and ortho-bromoanisole, which is minor product. Mechanism: Cl2 plus FeCl3 Br plus FeCl4 minus, and also C6H5OCH3 plus Br plus gives C6H4OCH3Br, that is ortho-bromoanisole, which is minor product, and major product is para-bromoanisole. Consider the reaction C6H5OCH3 plus CH3Cl in presence of anhydrous AlCl3 or CS2 gives 2-methoxytoluene, that is minor product, and also 4-methoxytoluene, which is major product. Consider also the reaction C6H5OCS3, that is anisole, plus CS3COCl, that is ethanoyl chloride, in presence of anhydrous AlCl3 to give 2-methoxyacetophenone, which is minor product, plus 4-methoxyacetophenone, which is major product. Nitration. Anisole react with a mixture of concentrated sulfuric and nitric acid to yield a mixture of ortho and para-nitroanisole. Consider the reaction C6H5OCS3 in presence of H2SO4 and HNO3 to give 2-nitroanisole, which is minor product, and 4-nitroanisole, which is major product. HNO3 plus H2SO4 reversible gives H2O plus HSO4 minus, which in presence of H2SO4 gives H2O plus NO2 plus HSO4 minus, where NO2 plus is electrophile, which attacks on anisole, and electrophilic substitution takes place and forms 2-nitroanisole, which is minor product, and 4-nitroanisole, which is major product. Let's understand preparation of ethers. Method 1. By dehydration of alcohols. Alcohols undergo dehydration, that is removal of water, in the presence of protic acid, that is H2SO4, H3PO4. The formation of product after dehydration can be ether or alkene depending on reaction conditions. CS3CS2OH, that is ethanol, at 443 Kelvin in presence of H2SO4 gives CS2 double bond CS2, that is ethane, and at 413 Kelvin and in presence of H2SO4 gives C2H5O C2H5, that is ethoxyethane. The formation of ether is a nucleophilic bimolecular reaction involving the attack of alcohol molecule on a protonated alcohol. Consider the reaction CS3CS2OH plus H plus gives CS3CS2H2O plus, and also the reaction CS3CS2OH plus CS3CS2H2O plus gives CS3CS2OH plus CS2CS3 plus H2O, and CS3CS2OH plus CS2CS3 gives CS3CS2O CS2CS3 plus H plus. Text. The method is suitable for the preparation of ethers having primary alkyl groups only. The alkyl group should be unhindered and the temperature be kept low. Otherwise, the reaction favors the formation of alkene. Dehydration of secondary and tertiary alcohols to give corresponding ethers is unsuccessful as elimination competes over substitution, and as a consequence, alkenes are easily formed. Williamson synthesis. It is an important laboratory method for the preparation of symmetrical and unsymmetrical ethers. In this method, an alkyl halide is allowed to react with sodium alkoxide. Rx plus R-ONA gives R-OR plus NaX. Ethers containing secondary or tertiary alkyl groups may also be prepared by this method. The reaction involves SN2 attack of an alkoxide ion on primary alkyl halide. Consider the reaction CCS3 whole thrice O minus Na plus CS3Br gives CCS3 whole thrice OCS3 plus NaBr. Alkyl halide should be primary because elimination occurs for secondary and tertiary alkyl halides. Tertiary alkyl halide form only an alkene and no ether is formed. This is because alkoxide are not only nucleophiles but strong bases as well, leading to elimination. Consider the reaction CCS3 whole thrice Br plus OCS3 minus Na plus gives CCS3 whole twice double bond CS2 plus NaBr plus CS3OH.